So today we have Isamu. He's gonna present what's hidden in a randomly weighted neural network. I think what's what was really interesting is Isamu, you're a freshman here,
Yeah.
right? And in the undergrad program. I don't even know how you got into this group. This is sort of a graduate level group, but we're happy that you're here and contributing. Thanks. So then also one other note is that we do have, I've been posting these on YouTube, so I have permission to do that. So check it out, and hopefully some of you can send me some more paper topics. I think Hunter, are you? No, you're not next. Pavan's next, and then you're after. Okay, great. Thanks. Take it away.
Okay, hello. And so the background behind me kind of like looking at this paper was mostly because I was kind of working on Typography, like the data science competition thing. And it was like 3 days before the deadline, and I had nothing. So basically, I wanted a way to kind of train a network really fast with, or actually, I wanted a way to train a network without spending time, or kind of like a new way of training a network. And I found that kind of like an interesting paper like this. So I implemented. Well, I kind of like use a code that they had to implement it. So it was kind of fun. So anyway, the basic idea of how we make neural networks learn is quite simple. Like there's this loss function, and we kind of like start off with 1 point, and we just kind of like, we just subtract the gradient, and the theory is that we end at the local minima in the end, or the global minima, and then basically we have the best network after like millions of hours of training. So actually this paper wasn't the first paper of its kind. It was actually the second paper. The first paper of its kind came from the lottery ticket hypothesis. So, hello. So basically what this paper was it was given by MIT, and they had this hypothesis. And in that hypothesis, they said, well, kind of like training the whole network is a bit silly. So we just kind of like, maybe there are some lottery tickets in the net. Basically what that means is that, like given the whole net, we can kind of like select a few networks inside that kind of like entire net, and we can just use those winning tickets to kind of like get comparable performance to the actual net. So the way they did this was quite simple. First they randomly initialize the neural net and train it. And then they kind of like select the top kind of like P% of the largest weights in the network. And then they just select those. So basically, what they did is like they selected the top 10% of the weights, and they just trained on those, and they kind of like looked at the result. Yeah, I forgot to say. They got the first 10% of the weights, but then they reset the weights to random values, and they kind of like just trained on that. Any questions so far? Okay. So what they found was that they kind of like had comparable performance. Like this is like, this percentage denotes the amount of weights remaining. So like this is 1.9% of weights remaining, and like it still got like 97% accuracy, and some bit that very a bit better than the actual fully initialized 100%. But yeah, that's kind of interesting. But yeah,
For this specific paper from MIT, what was the data set that they were evaluating? Was it
I think,
CIFAR 10?
yeah, I think that's yeah. But anyway, recently, kind of like they found a rather more interesting kind of idea, and it was that even without any training, we can find in like a randomly initialized network some kind of like pathways that are kind of like that are lottery tickets from the start without any training. So basically, we can train on a network where we freeze all the weights, but we can still get kind of compatible performance. And this method is called the edge pop-up method. So it kind of like just pop-up, makes those kind of subnetworks pop up. And yeah, it's kind of like a nice way of saying it. And the main idea behind this is they use scores. And so basically what they do is that you have the weight, right? So you initialize kind of like randomly initialized. You can choose the distribution, but basically it's randomly initialized kind of like a matrix that is the same dimensions as the weights for every single weight. And then we select the top k% of weights, and then we only update the scores. We only update the scores. We do not update the weights. We just update the scores here. And then the final thing we do is that given the top few percent of those kind of scores, we just select the weights that correspond to those scores, and we kind of like we set all the other weights to 0 basically, and then we kind of like do the matrix multiplication, and then we get the result. The way the scores are updated is actually simple gradient descent. So the question is, well, yeah, these are the few implementation points. So only the top scores pop up, and the weights are not updated, and the weights that are not at the top k% of the scores are set to 0. So the question is, well, why does this work? Like we are not kind of like touching the weights or anything, and we are just kind of like updating an arbitrary thing called scores. Like, why does that even work? Well, the question is, it's because it's kind of like the same as gradient descent. So now we will go into the math of things. So basically, this is the output from. Basically, this is the output from a kind of like a single neural net. So basically, here's the input and here's the output from a single like matrix multiplication. And yeah, and this is the input and this is the weights, and this age corresponds to something that is like basically it's a mask. It's 0 where the scores are kind of like smaller than the top k%, and it's 1 at the point where the kind of like the scores are kind of like at the top k%. So then we kind of like approximate the gradient like this. The reason we approximate it is because this age is it's kind of like you can take the derivative of a discrete function like that. So you need to approximate it some way, so we can just kind of completely ignore it like that. And so, well, just simple chain rule tells us that it's kind of like the same as the derivative. So it's a gradient for the scores. So we can take the derivative of the loss function. Sorry, this is the loss function with respect to the derivative of SUV. So this is the scores at the edge U to V. And yeah, that will be this. Well, kind of like we just set this as a, we just kind of make it so that we multiply this by SUV. Yeah. Any So, okay.
What is the loss here? Is it classification?
Yeah, it's classification. So it's the actual loss of like, yeah, there's no difference there. And finally, we do gradient descent and peaks. Yeah. So basically, we update the scores like so.
I have a quick question.
Go ahead.
So the idea is to, instead of updating the weights, you're finding out a selection criteria to select weights to.
Yes.
Okay.
Yes, it's kind of like finding the. It's like finding a lottery difference, right?
Aren't you just using? Aren't you making it more complicated? Not you, but aren't they making it more complicated? Because you could just backprop on the weights without the mask, and so you're adding a masking term just to show that you can do this.
Yes, I won't say that this research is practical, as I found out, but the main idea is that you can kind of like find these kind of like weights in seemingly random kind of initialized neural network. So I think the problem is with the kind of like method of finding those kind of like weights, and also kind of like it's a bit faster than actual training because you can freeze all the weights. So when you freeze all the weights, it's kind of like, well, I'll show you later, but when I train it, like, when you usually train it, that like takes 35 seconds to effort. I train a cipher 10 with ResNet 18 or something. But when I actually use this, I get like 28 seconds per effort, and it had kind of like a bit of, it has similar performance. So it's kind of like a slightly better strategy, I think. But anyway, well, kind of like even if we say we use gradient descent on these weights, it still does not answer the fundamental question, I think, of the why kind of like updating these weights and updating these scores and selecting the top K% leads to, I don't know, leads to kind of like them kind of like finding the weights that actually matter. So basically, they have this theorem. So when HIP replaces HJP, basically the score at JP turns out to be larger than the score at IP, you kind of like replace the weights like that. So you set the score at IP to be 0, where the coefficient that you multiply the weight that's IP by 0, and you kind of like set the weight at JP to be 1. And then you kind of like just go like that. So, yeah, the math here is a bit more interesting. And basically, yeah, this means that the score at JP, so the HJP, is greater than the score at IP. And if we go back a bit, we know that the updated value of these kind of scores kind of like, that means that the updated values of the score at IP is kind of like a bit, oh yeah, so before the update, we can say that sorry, I kind of like messed up the terminology a bit. So before the update, we can say that the score at IP is larger than the score at P. And after the update, we can say that the score at P is larger than the score at IP. So when we look at the gradient descent, well, if we were to say that we update the scores, we can say that we can come up with this equation because the score at IP is larger than the score at JP, and if we take a negative here, we can say that score at IP is greater than the negative score at JP. So when we look at the gradient thing, so if you look at the gradient thing, we can kind of like see that the gradient that score at IP, the negative score at IP is greater than the gradient that score at JP. Yeah, I hope I'm not missing anything up. Is there anything kind of like seems wrong to you? Well, so next, kind of like the authors came up with this interesting strategy of using a Taylor expansion. So the Taylor expansion where we kind of like expand that A is like this. We take f of A, which is a constant, and the derivative of f, and you can input A and x minus A and so on. But kind of like in physics, they just take the first term, the first derivative term. So this is a way to approximate like f of x or something. So if we kind of like go back a bit, or not here, we kind of like set LP to be this way. So when we look at here, we can say that the updated value of LP minus LP is kind of like, since we kind of like replace the edge at IP with JP, we kind of get something like this. So the input of zeta I times the weight IP minus the weight at JP times zeta J, because we kind of like replace the scores there. Like we kind of like set that this score to 1 and this score to 0. So then, when we want, if you want to, this is the loss function. If you want to kind of like Taylor expand the loss function at this updated value of LP, kind of like we can kind of like write it in this way. So what's interesting here is that you can actually write it like in a Taylor expansion like this. So start at this constant and subtract this constant. So we kind of say that we start at this constant and we subtract this constant like this. And we get this. So as it turns out, the loss at LP, since this is always kind of like lower than 0, since we kind of like said since we already know that that kind of like this is greater than this, we can say that this is smaller than 0, like this. It's kind of like, yeah, it's a nice mathematical trick, I think. And then in the end, we can say that the loss at LP, the updated value of LP is lower than the loss at LP, the previous value of LP. And yeah, I think I messed up some kind of like terminology here because I was a bit confused by the fact that the updated value of IP, but what I assume to be the updated value of IP is greater than the updated value of SGP. Yeah. But I think, so sorry about that. Yeah, I'm still a bit confused about it because before this it makes sense. Sorry. Well, anyway, now we kind of like, we started kind of like it works for actual kind of like matrix multiplication, kind of like fully connected layers and stuff. So now, well, does it work for convolution? So when we kind of like do convolution stuff, we kind of like put a kernel of a input image like this. So, and this is an amazing article on towards data science. So, and I recommend you to read it. But basically, you can like put the kernel kind of like this input value. And the interesting thing is you can kind of like represent it as a single matrix multiplication. So if you just assign scores to every single value here, the order-based conclusion is that you can kind of like use this for the convolution too. And well, these are the references, and they are amazing. This is the lottery ticket hypothesis one, and this is the actual paper of random networks, and that's where the image came from. So anyway, let's test it out. So thankfully, the authors have this GitHub repo of hidden networks. So this is one of the authors, and the Vivek Ramanujan was the one that kind of made this repo. And basically, the instructions on what to do and stuff like that. So I kind of like follow your advice, and I kind of like use weights and biases. And so I kind of like, I use collaboratively. So sometimes the 2-minute kind of connection 2 minutes and stuff. So kind of like sometimes you see these pathway down ones. But the interesting thing that I found was basically this green line here is the one where I kind of like just ran it on a regular. This is like I trained on a Cipher 10 network with convolution and stuff. And what I found was that the normal network is still has kind of like very little performance. I should kind of talk about the accuracies here. So this accuracy here, the current accuracy at the top 1% means that kind of like in a Cipher 10 data set, what you do is that given an image, you kind of like predict what it is. So basically, you have all these categories. And basically, what this does is that it says in the top 1% of our predicted categories, if the thing that they say that it is kind of like if it's an image of a cow, if we say that in the top 1% of the categories that is a cow, then we say, yeah, we did a good job. Here, we say that if in the top 5% of our predictions there's a cow, we kind of like say that we did a good job. So, yeah, then you kind of like do a usual neural network, you kind of get like 99.9% of the accuracy here, and 94.62% of accuracy. And this is a subnetwork where I kind of like only print 10% of the weights. So like 90% of the weights remain, and I kind of do the same thing. And yeah, the performance is like, it's quite good, like, but it's kind of like basically meaningless because like 90% of the weights remain. And then I kind of print 50% of the weights and get something like this. So it's slightly worse than the 90% one. The interesting thing I found was that in the beginning part, like the 90% one or the 50% one slightly outperforms the usual run all the time. And when you go to the 80% one too, it also slightly outperforms the normal run at the beginning. So while it may not be kind of like actually, completely revolutionary, kind of like, I think it's kind of like a bit interesting that the more you prune the weights, if you want to train for like a really small amount, like, I don't know, 5 epochs or something, you can get like, I don't know, 70% of accuracy with a network where you kind of just select the random weights. Yeah. There you go.
So just to clarify, is it top 1, as in it's the top, or is it top 1%?
Top 1%. Yeah.
So what is the network here? Is this ResNet?
Yeah, it's ResNet 18.
18.
Oh yeah, I forgot to show you the source code for the actual kind of like subnet thing. I actually kind of like, I didn't understand the paper initially, but after I looked at the source code, I was able to understand it a bit better. So basically it's here. And this is the code for the subnet. Coded in PyTorch. So, and this is the scores. And we kind of like initialize it based on timing, no, uniform kind of like normal distribution. And basically here's where you kind of apply the weights. So the thing that is interesting here is that you kind of like you do not actually update the value of the weights, but you just kind of like multiply it by the subnet here. And it's kind of like get subnet.apply thing is up here. Basically what it does is it sets the indices before j to 0 and after j to 1 like this. So it's kind of like selecting the top k%, I think. And then it's just kind of like, that's the convolution function with this updated weights like that. Yeah, sorry about the confusion of the math. I seem to be not not that competent in that, but yeah. So any question? Yeah.
For the lottery ticket hypothesis and this work, how sensitive is the result to the initial distribution of weights? Like I suspect if you have like some point mass of weights, it's obviously not going to do well.
Yeah, that's kind of interesting. So on the GitHub repo, he actually addresses that, and here's the kind of result. So basically, if you kind of use a normal distribution, kind of like the accuracy is really lower than the signed Feynman normal constant. So basically, what this the signed Feynman does is it kind of like takes the absolute value of the weights, and so, for some reason it kind of works better than the initial distribution. So yeah, kind of like that's a really good point because it doesn't work with kind of like maybe a normal distribution or something like that.
So, something like this. You say top 1%. What does that mean? Because CFAR 10 has 10 categories, right?
So in that case, it's like the first category, I think.
It has to be the first. It has to be the top category.
Yeah.
Yeah. Okay.
Yes. Sorry about the confusion. Yeah. Yeah, I think that's the case. Any other question? Oh yeah, kind of like it wasn't useful for my cargo thing, but yeah, it is a bit of an interesting paper. So yeah, and the math before I was confused was really amazing. So yeah, maybe you can, some of you can research a bit more on this topic to find a better way to kind of find those lottery tickets. Maybe. Yeah. So that'll be the end of my presentation. Thank you.
Thank you.